introduce Professor Gregory Voth from University of Chicago. So thank you.
Okay. Well, thanks for coming, and I'm sorry it's a Saturday morning. I'm sure that you would prefer doing something else than listening to me, but I will do my best to keep your interest. I'm going to talk about coarse graining and approach it from what we call the bottom-up perspective, which is more fundamental, I guess, than parameterizations. Try to figure out how to take molecular interactions and translate them to these coarse-grained models. And then I want to give you a flavor for what the frontier of these things are, like where we are right now in terms of, the challenges, how far we've come with that, and what some of you might be able to do in the future, okay? And then Alec is here from my group to do the tutorials after. He's going to show you some of the aspects of our software, which we've been working hard. We realized about a year ago, or maybe a couple of years ago, that we had been really bad about preparing software for the general community to use. We were very much interested in solving actual problems, not so much producing software. And also in the United States, you don't get funding for software. It's a terrible flaw in our system, but you can write a grant saying, I'm going to make software for hundreds of people, molecular dynamics or whatever, and they won't fund it. So that's a problem. Okay, so here is what I'm going to tell you about. That's a whole bunch of things. We'll see how it goes. If we get tired, I'll just stop if you get tired. But here's sort of what I want to touch on. Just so keep this outline in mind, and I'll sort of come to these bullet points as I go along to highlight things for you. I want to give you sort of the background of what is meant by bottom-up coarse graining in an ideal world, what you would do if you could, maybe. I think it's probably to this day, the way this is discussed here is probably the best way, but that doesn't mean it's the only way. And then I really want to hit on something that is really critical, because coarse graining is simplifying a physical problem, right? And I think you're all kind of familiar with that, into a simpler representation. But in doing so, you're going to lose something, right? You're going to lose information. And we call this missing entropy. And I want to talk about progress we've made in terms of understanding that. Now, I also want to talk about the issue of coarse-grained dynamics. And I think many of you may realize that when you run molecular dynamics programs, so probably the favorite one is Martini for a coarse-grained model. You have a time step and you integrate that, but that's not time. Okay, that's not the real time. That's not experimentalist time. That's coarse-grained simulation time. And there's a critical issue of how to connect coarse-grained models to real time. Okay, and then we'll see how all this goes. Solvation is a huge issue. I actually believe that just no one has dealt with this in the best way yet. The problem is simple. If you do molecular dynamics simulation of something in a box, as it gets bigger and bigger, that thing, there's more and more solvent, and your computer gets choked by summing over interactions between solvent particles. And then the thing you care about is far less of the numerical effort. So I think going into the future, we need to revisit this issue and basically get rid of solvent. We need the solvent to be implicit in the coarse-grained models, not like the old implicit solvent models, but new ways. So I'll talk about this. Then these are more interesting, exotic frontier things. One is, if you have coarse-grained models and you've made them pretty coarse, I don't think anyone to this day has a very good way, at least from a bottom-up perspective, of building large-scale conformational change into those models, right? So for proteins, the domains move around. So we've done a little bit of work on this. And then finally, my favorite thing is the concept of ultra-coarse graining, which is an abstraction of coarse-grained models, of this bottom-up picture of how we can make them have more information. Okay, but still get very aggressive in the coarse graining. So this is a lot for you to listen to on a Saturday morning. Let's see how it goes. And if I'll probably get tired before you do, so you can not be afraid that your brain's going to get filled too much. Okay, so coarse graining, I've shown these slides hundreds of times. You know, the big issue is, well, there's two big issues. One is, what do you want to do with the coarse graining? Well, bottom-up coarse graining is to try to stay true to some sort of a theory, right? Statistical mechanics is the best one. I will point out, and this is yet another frontier, which I won't even really talk about. This is equilibrium statistical mechanics. Not very many people at all have thought about how to do this for non-equilibrium systems, especially when you're really way far away from the linear response regime, right? So simple linear response theory is failing, you're really out of equilibrium. But, you know, I'm going to start here. This is sort of how we do this, okay? You imagine you have functions that do mappings of the atoms into the coarse grain sites. And this is already a bit of a challenge because you might imagine that you want grain representations to go beyond just these atoms that you have. I'll talk about that in terms of representing solvent or other things. But as a start, let's imagine that we do these maps. These are simple mathematical functions. There's one for every map. Center of mass works pretty well. For example, the side chain, the backbone, you can see this little hairpin. So the way you do this in stat mech, it's a trivial approach. This is putting in unity into this equation. And it should be understood that this is a product of many delta functions, right? Many mappings, not just a single one. I didn't write the product there. It just makes the equations messier than they need to be. Then what you do is you switch the order of integration. You do a subtraction. And what you see is, well, if you want to maintain consistency, not for, you know, one number equals another number, okay, but for every distribution, so every possible orientation of the coarse-grained particles, that should always be 0, then, you know, that you didn't accidentally pick the mapping, you didn't accidentally pick the potential energy so that it's 0, but it's always 0. The only way that can be the case is if this integrand is always 0, right? And if that's the case, then what bottom-up coarse graining tells you is something profound but also very painful in a computational sense, and that is that this coarse grain interaction is really a free energy function. It's a so-called potential of mean force. And it's also a function of many variables. You know, we're kind of used to, in free energy sampling, you know, Michele Paranello is here. I've done work on this. Many, many people have worked on this. You're used to looking at one-dimensional, you know, free energy surfaces going over a barrier, increasingly two-dimensional, right? Maybe a few more if we use machine learning tricks. This is really very high dimensional still. This is, you know, imagine that you have a lot of these hairpins. There's many, many coordinates. There may be solvent, et cetera. So this, even though it's fundamentally important, is incredibly difficult to calculate directly, all right? And, and actually, what Alec will show you students is what I'm about to show you next is sort of one approach to this. Now, but this is profound because in the bottom-up perspective, what that says, you're averaging over, in the Boltzmann distribution, over these atomistic motions and projecting them onto this coarse grain. So that's got entropy in it, right? So this is not a potential energy function. This is a free energy function. And so I want to show you sort of how this works out in a minute. Now, how do you get around this thing? So here is the divergence of sort of the top-down, bottom-up perspective. And then there's things in between, right? So the top-down perspective is, you know, don't try to do this. Just start with these things and try to parameterize them somehow. You know, what Martini does is transfer free energies between, I think, octanol and some hydrocarbon or something, and then you can supplement that with some targeted MD different things. And then the bottom up is, well, figure out a way around this direct attack on this incredibly hard problem. Okay, so that's what I want to tell you about for the short run. Okay, this goes back now nearly 15 years. It was actually an early form of machine learning. Since everyone's using, like every bloody day I open a journal, I see the word machine learning in there. This was machine learning. So what we imagined was we want to do some cost function, a residual. We don't know the coarse grain interaction. We imagine we can represent it somehow. We do imagine that we know the atomistic forces, that we have a force field that we can trust. This sum over these alphas is the sum over the coarse grain maps. You square it so it's always positive, and then you have some sort of an ensemble average. And this is a really interesting important and slightly depressing question is how extensive does this ensemble average need to be? Because if you could do the whole ensemble average, you wouldn't need to do the coarse graining. So there's kind of a paradox there, right? And I think this is a place where modern techniques that are developing in machine learning, you know, for exploration and learning, that these can come in as help us understand, you know, how much data do we really need to get a good coarse grain model? Okay, this is, you know, if you're not asleep, this is basically a least squares fit, right? Squaring that, summing over the sides. The tricky part is this projection, the changing resolution here, and this ensemble average. But you can prove, this was done in 2008, well, actually 2007 in a paper I didn't show here, that if you can represent the coarse grain interaction perfectly, right, which you can't, you don't know what it is, but imagine you could, you'll get the exact answer, right? Okay. It's like quantum mechanics, right? We never know the wave function. So we use the variation theorem to you know, we guess a wave function, we optimize it. You don't know what the right answer is, but if you work harder and harder at a more elaborate wave function, you get a better and better answer. Okay, what Alec will show you in how to use is how we made this work, which we called multiscale coarse graining. The idea is we start with atomistic forces, we go to coarse grain, which is another scale, and then you take the coarse grain model, you go simulate things at even higher scale. So that's the idea of multiscale. You have to represent the interactions in some way. They don't have to be pairwise decomposable, but that helps a lot. In the tutorial, you have some simple systems, I think ethanol or methanol, just learning about this. And then this was where the machine learning came in. If I had, you know, if I could translate in time 15 years, I'd be doing this with deep learning now, right? Rather than things like spline functions or wavelets or things like that. I mean, in fact, Frank Noy and Cecilia Clemente have just come out with a paper basically doing this force matching with deep learning. And it's got some very powerful aspects to it. But at the time, we numerically train these sets. So that's what will come up. An alternative method that I really do need to mention, it's complementary, it's also very insightful, I think, it was something that Scott Schell came up with based on relative entropy. Now, Scott, of course, didn't come up with the idea of relative entropy, but he came up with the idea of using it to define coarse grain models. Same sort of idea, that you have maps of the atomistic things, and you want to minimize the relative entropy between your model system, your coarse grain system, and your atomistic system. And you have to solve a set of equations to find the parameters of this. We kind of thought about this in the original days. I thought it would be too numerically difficult. I'm not trying to take credit for Scott's work. It was actually a slightly different variational theorem we're using. But it turns out, you know, you can solve these in certain cases. And Alec actually just published a paper in the Journal of Chemical Physics on using modern machine learning concepts for going sort of beyond both of these concepts. And so if you're interested in that, I think that's where things are headed. Okay, now one thing I do need to mention, I don't have time to talk about this, and sadly this paper has a few typos in it which we still haven't gotten around to submitting in erratum, but in case you do read this paper, just bear in mind I think there's a few sign errors and this and that we need to fix. There is a serious issue about what these coarse grain models actually mean and what they're representing, all right? Why is that? It's very simple. Observable properties in a real system, right? You start with quantum mechanics. The quantum mechanics, you solve the electronic structure. It gives you a force field. Sometimes we either do that directly or we model that force field. And then you have things that you want to calculate. And most often, or quite often, they depend on all the atoms of the system, or most of the atoms of the system. In coarse graining, you have eliminated many of those atoms of the system, right? You have this coarse grain representation. So this is what we call representability. The point is you cannot just treat these coarse grain particles as if they're physical particles. Plug it into a virial to calculate pressure, or you just can't do that. So you have two choices. One is to get more elaborate in how you do this. We just published a paper on this in Journal of Chemical Physics, I think the very last issue of JChemPhys. Or you can view the whole calculation as a model. This is sort of what the top-down model, top-down simulations do. Is you know, everything's a model. It's even the calculation of the observable is a model. It's not connected to any real molecular system. It's modeling it. But this is a very deep problem, and I could spend an entire day talking about it. If you're interested, you might read this paper. Okay, so let me quickly show you how this kind of manifests, and again, you'll get some direct numerical experience. It really, this thing which I've talked about for a lot of years, really illustrates the concept of bottom-up coarse graining and how it works, even though it's for a problem you wouldn't necessarily want to do. And that is to take a liquid of water, not just one water molecule, with the whole liquid, and turn it into a liquid of one bead particles, you know, as if they were argon, all right? And so, so you do all this algorithm that for many of these in the liquid, not just a single one. And the problem is you know, any kind of empirical modeling of a one particle fluid, you know, you're not going to be able to guess what this interaction is going to be that makes it behave like it's water, all right? And this representability problem has already manifested itself because, you know, these things no longer have dipole moments, right? You've gotten rid of the OH bonds, so there's an issue of what can you calculate. Well, one thing you can calculate is the structure of the fluid, right? The basic sort of tetrahedral structure. And so we can do this. We feed this through the algorithm, and this is the G of R function, the radial distribution function. This is some number of years old, but you can see that you get it. And what's remarkable about this is that the physics of water with the tetrahedral coordination, the hydrogen bond, you know, water is an expanded fluid. It's not a dense fluid. That's all translated into this one bead model here that when you do this integral over that, you get fourfold coordination. That's very hard to do. A Lennard-Jones fluid or something like argon always has 12 neighbors. It's defined, its structure is defined by packing, by the hard wall packing. So the question is, how does this physics and this bottom-up approach manifest to give you a one particle system, you know, fluid, that can behave like water structurally, all right? And the way that does that is we go through this algorithm. We do what was called force matching. You get a pairwise representation of these interactions. And this is what the things look like. They look very unusual. This is, again, pairwise interactions between the particles. This is one of them here. And that, for your eye, is a Lennard-Jones interaction. You can see immediately what happened when I coarse-grained real water, that the physics that causes it to be a tetrahedrally coordinated fluid with a lot of sort of open motion appears in this knotty kink right there, okay? Because a simple fluid, that hard wall, the 1 over r to the 12th van der Waals wall, is the thing that gives you the packing, gives you 12-fold coordination. So when you coarse grain the physics of water into one bead, you get that kink. And actually, that's an entropic effect. This is not a potential energy. This is the entropy that is inherent in water that you know, fights off all these interactions, that stops it from packing, that makes it fourfold. It pops up there. This deep minimum is responsible for giving you the higher solvation shells. So you can see the physics of water, for the most part, appears in this approach, okay? Now, I would have challenged you, if you've never had thought about this problem, never had an algorithm like that, to guess that potential, right? To try to, you know, try to make a one particle fluid act like water, right? It's not so easy. And there, actually, history is full of attempts like that. All right, so what did I mean by what I just said? Bear this in mind. The coarse-grained potential in a bottom-up thing is really a free energy function. You're going to represent it in some way, as in a simple case, by pairwise interactions. In a more complex case, of course, you'd have bonded interactions and so on and so forth. If that's free energy, it's got two pieces. So it's got an energetic or enthalpic part, depending on what ensemble you're in, and an entropic part. And the entropic part is basically, this is a finite difference, is basically a temperature derivative of this. So actually, this entropy appears, if you do a good job of this bottom-up coarse graining, this entropy that is missing, that is eliminated from the problem by coarse graining, pops up in this effective interaction via a temperature derivative, right? And the first time we actually mentioned this was in 2011. Will Noyd has written some papers on this, and so have we just recently, and I'm going to talk about that now, okay? So where do we stand? Bottom-up coarse graining, we understand it as, you know, sort of the physicist's approach of integrating out motion, right? Physicists are very commonly used to integrating out fields or things that are coupled to particles. We're integrating out a lot of high-frequency atomistic motion, folding it into these coarse-grained interactions. You can see the difficulty of approaching this kind of thing from the top down. Although there's hope. We're preparing a paper that perhaps top-down modelers, right, could start focusing on not just, what is some effective interaction, but the pieces of it. Because by basic statistical mechanics, we know that there's got to be an energetic and an entropic piece. So maybe this is what should be fit here in a top-down approach, okay? So what about this missing entropy? Well, I'm going to show you an example and how this kind of works out. This is methanol, right? My chemistry. The day I can't identify that, I should probably really hang it up. That's methanol. Okay, I'm gonna illustrate this through coarse graining methanol, fluid of methanol, into one bead particle, just like I was telling you about. Now, that's a good illustration. By the way, this is not in press anymore. This is published in Journal of Physical Chemistry Letters, actually. You can see curves that kind of looked like that water example. Methanol is slightly different. And what I'm showing here is for methanol, and there's chloroform also. This is the entropy contribution. I think the dashed line is scaled. This is the pairwise energy contribution, all right? Now, the reason I focus on this problem is that you can understand physically what's missing in your coarse-grained model, right? Because this particle, the atomistic representation, has translational motion, and not simple translational motion. They hit each other. Rotational and vibrational. When I coarse-grain it to single beads, these latter two things are gone, right? Physically, they're not in the representation. So the question is, can you recover them? Can you recover them in the coarse-grained interaction, right? So you probably don't want to focus on this right now because it's complicated. Basically, it's not hard. It just says do this at multiple temperatures, okay? So what it is, you run all atom simulation. I'm showing you how to do this. You develop coarse-grained models at different temperatures. You take the temperature derivatives and go back, and this is the thing we're interested in. This is the so-called mapping entropy or missing entropy. And the question is, can we recover that? Can we recover that by looking at these temperature derivatives of the coarse-grained interaction? No one likes to look at a lot of tables, but for a simple fluid, you can actually calculate the entropy as an average over the structure, the radial distribution function. And you actually see that, it's really not so bad. So if I look at calculating the missing entropy, this is the all-atom result. And I should qualify that there is no exact way to calculate these entropic components at the all-atom level, right? We're using an approximate approach. I think Goddard developed this some years ago. But you can see that when I coarse grain things, what I get here is this is the rotational vibration. This is the sort of the calculation of the missing entropy from the temperature derivatives. This one is not perfect for methanol, but for chloroform, actually, it's quite a bit better. So you can actually really recover that missing entropy. What do I mean by that? What I mean by that is it's not missing, okay? What I mean by that is the entropy of these motions of rotation and vibration, when I do this bottom-up coarse grain, actually are in the effective interaction between the particles. And I, through my best estimates, can actually recover it within, it's not exact, but pretty good. Okay, now why do you care about that? You care about that because if I want to develop a bottom-up coarse-grained force field that can be used for a lot of systems without having to do it all over again, right? You'll see the code. You can use this code. You can download the code in the future. But most of us want to believe in something called transferability. We want to believe, and actually there is no transferability of anything, but we want to believe in it. Okay. So what we would like to do is take a coarse-grained force field and apply it to a new system without redoing the whole coarse graining, all right? And so that's called transferability. Now, the reason that this is important, the energy piece is probably going to be fairly easy to represent by things we understand, okay? The entropy piece is going to be complicated. And the question is, if we can get a handle on this entropic piece of these interactions, maybe it will allow us to develop coarse-grained force fields. I don't know the final answer to this. I think there's promise there. Let me show you. So what I'm going to show you here, and again, it's in this paper that came out, is if we take bulk methanol and bulk carbon tet, all right, and carbon tet, chloroform, right, and we mix them, okay, and I don't want to coarse grain this. I only want to coarse grain these, and I want to do it once. Is there a way to use what we understand about these pieces of these interactions and build a coarse grain model without doing it all over again? And it turns out that actually there's some things that work, things that are fairly standard in molecular modeling. One is the energy modeling. As I said, I won't go into the details here, but you can come up with an interaction based on the shape of these molecules that's pretty obvious. But the important part is the mixing rule. This is a standard mixing rule of interactions. We can apply these entropic terms that we calculate, the missing entropy piece, and do a mixing. It's basically a product of them and take the square root, okay? And when you do that, it actually works really well. This is the structure of the fluid. The structure is not perfect, but this is more telling. When I look at a mixture, right, this is a bit of a heterogeneous mixture, I get clustering going on, right? And so these are two ways of representing the clustering. This is observation per time, and this is the overall observation. This is a logarithmic thing. And look at this. So it actually, the mixed coarse grain thing compares, and that means transferred from pure fluids, compares very well, except maybe way out here in the tails with an all-atom thing, but over multiple orders of magnitude. So the clustering is rather different. Methanol's clustering and chloroform's clustering. So I'm pretty enthusiastic about this. It's going to take a whole lot of work. It's going to take other people that have the dedication to want to do bottom-up coarse graining, right? They don't want to just skip things. They want to actually try to get that entropy in there. But I actually think that we might have had a breakthrough here. Okay. Okay. Are there any questions? By the way, if you have questions, stop me. I'll be happy to tell you. All right. I'm going to skip a little bit into the issue of dynamics. The reason I'm going to do this is because I just got finished telling you that maybe we have a way of capturing this mapping entropy or missing entropy that is really not missing. We just need to extract it out of our models. And I want to show you that it may give us a handle on dealing with this dynamics problem. Right? The dynamics problem is a serious problem. The way that we typically deal with in statistical mechanics the notion of eliminating degrees of freedom is a very famous formalism called the Morey-Swansig formalism. I don't know how many of you know about that, but the Morey-Swansig formalism is if you have a fully resolved system and there's some pieces of it you want to focus on, it shows you how to eliminate the degrees of freedom of everything else. And it's very hard to do it in generality. You use these projection operators. If you make a bunch of approximations, you end up with a generalized Langevin equation for your remaining particles, okay? And I mean a lot of approximations. There's problems with this. First of all, just mathematically, it would be very, very hard to do that. We wrote a paper on it, but other people are trying to do this. Just to do it in generality would be very hard. Then there is the issue that if you have done this, the resulting equations of motion have a friction piece, right? That's a Langevin equation where the particles move and there's some sort of friction on them, and a random noise piece, okay? That will slow down their motion. The whole point of coarse graining is to simulate faster and more extensively, right? So that you can actually access larger scales. So if you have done some elaborate formalism to slow down your simulation back to basically the same sort of time scale as the all-atom molecular dynamics, you've defeated yourself. So even if you could pull this off, which is really the right way to do it fundamentally, you would have defeated the purpose of coarse graining, okay? So the question is, what's the alternative to that? Well, I don't know, actually. But I will tell you that what I think it is some sort of a theory where we go ahead and do the coarse grain dynamics, right? We do our coarse grain simulation. And then we have an additional theory that tells us how to scale the time scales of what we saw, all right? So, and we can do that if we're lucky from equilibrium properties, the things that we get from our simulation. That's if you're a simulator, you can imagine in your mind's eye, okay, this is what I would like to do. I'd do my coarse grain simulation. I'd get these data. I'd record it in time. I'd say, you know, this protein moves around on this lipid bilayer at this time scale. And then I'd have some sort of a theory that would correct that, right? That I would feed it through another theory. And we don't have that theory, okay? There might be, Joe Rodzinski in Mainz has done some very nice work on trying to use Markov state models for maybe rescaling coarse grain things. I'm going to get more fundamental about this and look at what we might understand even in terms of liquids. Okay, so this is what this part's about. In liquids, there's a really interesting theory out there that says the diffusion of the particles in the fluid is related to the excess entropy of the fluid particles. And the excess entropy is the entropy relative to the ideal gas limit. Now, those of you that aren't sleeping say this is never going to work with proteins and we're not interested in fluids. I agree with you. In other words, proteins have conformational motion. They have rare event motions. But I think this has the right spirit, all right? And I think it's a big step forward in going in the right way. Now, the excess entropy is negative. Why? Because the ideal gas is the most entropic thing you can possibly have. So the entropy of the real gas is going to be less than that, so it's going to be less than zero. So this looks like an Arrhenius law. You know, it looks like something where you have some sort of a limiting diffusion, and then it gets exponentially scaled by a negative number, and that slows it down, okay, the real thing. And why do I care about this? Well, actually, I can get at this excess entropy through what I just told you about in the prior part of my talk. And the question is, for a coarse-grained system versus an atomistic, a fully atomistically resolved system, is that factor, this empirical factor in this Rosenfeld theory, is it the same or different? Because if it's the same, I can get somewhere. If it's different and I don't know what it is, I'm not going to get anywhere. So that's a fundamental question. There's also this thing D0, which it might be the same or different, and it will be different probably between the coarse grain and the atom. But if the alpha is different, if your coarse grain physics is completely changed, so that even if this law still exists, alpha is a different value, then there's this hopeless. All right. It turns out, again, this is coarse grain, the same sort of thing. Coarse grain diffusion of methanol. We like methanol just because the algorithms that Alec will show you work quite well for methanol. You don't have to worry about those issues. It's a good, it's a bit complicated, right? It's an amphiphile. And so here's the deal. I'm going to calculate diffusion at fine-grained or atomistic level. I'm going to calculate at the coarse grain level. I'm going to apply this scaling law to both, and I'm going to try to see if alpha is the same. I know that the excess entropy will not be the same, right? That's what the prior part of my talk was about. And, well, I don't need to go into all this stuff. It actually turns out that alpha is the same, it appears. There was a paper published before this. Actually, we haven't published a paper, but I hope to soon. Because they couldn't calculate this excess entropy like I had showed you in my prior part of the talk, they actually made the assumption that they're not the same. It turns out that really the scaling of the alpha is very, very same. It's about 0.7, right? And not just for methanol, for multiple fluids at multiple temperatures. This is actually for water, 4 different water models. And the missing entropy, the thing that I was telling you is in coarse graining, is the thing that goes into the coarse grain interactions, is actually is the difference here. So actually, we can calculate this now. The thing we're working on presently is the intercept, but the intercept is in the limit. Any of these is the excess entropy goes to 0, right? So it's some sort of a limit near the ideal gas limit, which we believe we can come up with a fairly good analytical theory for it. Why do you care about this? It would give us a way, with at least diffusion, by taking a coarse grain simulation, doing this simulation, getting all the coarse grain data, then calculating this excess entropy difference and rescaling the dynamics. Provided the only dynamics you cared about was diffusion. And that is in heterogeneous biomolecular systems, of course, that's not true. But I think it's a very important start. It got exactly the spirit of what I was hoping for. Okay. I got to move along here. Okay. So this is how it works. This is 4 different water models, different values of diffusion coefficient, 5 different temperatures each. You can see the coarse-grain diffusion is always higher, and that's a coarse-grain system. It's smoother interactions, fewer degrees of freedom, it goes faster. And then when we correct, the corrected thing goes right on top of the fine-grained or the atomistic result. The atomistic result looks brown here for some reason, but it's actually supposed to look beige. You can see 4 different water moles, 5 different temperatures, this all holds. So I think it's a big, big step in the right direction of solving this dynamics problem. Okay. By the way, should we take a break at some point so people can use the restroom or anything? Or let me just cover a couple more things, and then I'll give people a 5-minute break. Yeah. All right. All right. So let's back up. We went through what bottom-up coarse graining is. There's a very good reason that it doesn't dominate the field, like, for example, the Martini model does, because it's conceptually complex, it's algorithmically complex, it's physically complex. But most of us, even my dear friends in Martini, Stuart, Jan, Merrick, say if you could do it this way, you would do it this way, right? So I wanted you to understand what this is all about. And maybe at the end of it all, these approaches will begin to overlap more and trade back and forth. But right now, this is quite different. Missing entropy, the stuff that goes away apparently when you coarse grain, is really critical. You want to get a numerical handle on it. That gives us a hook into dealing with transferability, so you don't have to coarse grain all over again, and possibly dynamics. Now I want to sort of finish up today. And by the way, if you're one that doesn't care about all this sort of fundamental background theory, I want to get to some applications of all this that are really enjoyable, I think, to the HIV virus. I think you'll enjoy that. This solvation issue is a very, very serious one, and I don't think anyone has dealt with it. The Martini model, if you're familiar with it, has beads that represent 4 waters, and sometimes people make those polarizable to do a little better, but there's something really unsettling about that, because you're missing an entropy, an exchange, right? If you've locked up 4 waters in a bead, they can't exchange. So there's something fundamentally unsavory about that, even though it helps. Also, there is no mapping. In other words, it's not obvious how to map a molecular system into those kinds of beads. So what do we want to do? Well, we would really like to get rid of solvent. And the idea there is to utilize what we call virtual sites. Now, what do I mean by that? If I have a physical part of a molecule and I coarse grain it, what does solvent do to that? Well, of course, it directly interacts with those particles. But more importantly than that, it creates effective interactions between those particles. So how am I going to represent that? One way is to try to directly build that into my coarse grain model. So the coarse grain model is already working really hard to deal with missing entropy. It's mapping entropy. It's trying to get effective interactions. You throw in on top of that, by eliminating solvent, the need through the direct interaction to mimic what solvent does. That's a lot, and it may even be physically wrong. So this is the idea of building other coarse grain sites that are virtual sites. In other words, they don't represent real pieces of the molecule. They represent other stuff. And if you think about it, if I have a piece of a molecule here and a molecule here and a virtual site there, that is effectively building in an indirect interaction or a higher order correlation. And that's what solvent does. For example, the hydrophobic effect, things like that. Okay, so what do I mean by virtual sites? This is a lipid. I use this as a good example. We especially want to really coarse grain these lipids. We don't want very highly resolved lipids because we want to go to very big systems. As you have heard before, there's two approaches. They're sort of probably the best known bottom-up approaches, the force matching and the relative entropy minimization. And what we want to do is use that to create virtual sites, which I'll show you in a minute. And here's the reason. If I look at these systems and I do coarse graining without that, the multiscale coarse graining, the force matching, can create a nice lipid bilayer. It turns out that relative entropy minimization doesn't do that at all. You can't get good bilayer. So what we want to do is represent the solvent somehow in there so that we can recover a wide range of behavior. And so the idea is to build in coarse-grained beads, okay, effective coarse-grained beads. And here's a picture. There you go. So the idea is to dangle on top of the physical coarse-grained site something that represents solvent. So this is, we're going to denote here by the SL, solvent-lipid site. So this is a coarse-grained site, not real piece of, not an actual part of the molecule. It's representing what the water solvent is doing to these things. And this is a bit of an elaborate algorithm. It took for the first time, again, I don't think you want to spend time thinking about this, but it took for the first time actually utilizing both force matching and relative entropy minimization. Right, so going back and forth between these methods. And I think that's really valuable because they have different strengths. The force matching is very good for representing where the forces change a lot, right? The relative entropy minimization is very good at representing the minima of the effective interaction. So it makes sense to kind of go back and forth. And so what we end up here in this algorithm here is 4 models I want to show you. One is the 6-site, so 6-site here, 1, 2, 3, 4, 5, 6, force matching and relative entropy minimization, or versus the 7-site with the virtual site, relative entropy minimization and force matching. And now, when you look at these curves, these are effective interactions between these coarse-grained particles. The dashed ones are the relative entropy minimization. The solid are multiscale coarse graining. This side is the 6-site. This side is the 7-site. You know, no one likes to look at all these curves, but the first thing that you see is that 2 basically exact methods give different results. Why do they give different results? Because you don't know how to represent the interactions perfectly. You just simply don't know what they are, right? You have to guess at that. And I think with machine learning and other sorts of techniques, we can improve upon that. But these are going to differ. And more importantly, there's some very subtle differences when we include this virtual site that lead to quite different important differences in these baselines here, okay, in these mid-groups. And what that basically does for you is it allows very nice self-assembly behavior of these things. I think there was supposed to be a movie there, but it's probably missing. Anyway, it doesn't matter. Very nice representation of the bending modulus, so much, much better, closer to experiment. There's the movie. And also a wider range of exploration of possible conformations, right? So phase space. So we can actually assemble bilayers. As we change concentrations, we can get different sorts of structures. We can make predictions. This is as a function of concentration of lipid, you know, all kinds of things. And people actually see these things. So by simply representing the solvent by one virtual site, okay, in these very coarse-grained models, the richness of what solvent does, of amphiphilic assembly, comes out. And I am really very enthusiastic about this idea. Again, this paper that Alec wrote that's in Journal of Chemical Physics uses machine learning methods to sort of circumvent some of the approximations we had to make in this work here to actually potentially define virtual sites, and more than one. So I think there's great promise for extending this framework. So not just do bottom-up coarse graining of the molecules, but include the solvent, but eliminate the solvent represented by implicit particles and that have actual mappings to real interactions. And we're working and thinking about doing this now for proteins, for example, because you all know that solvent is really important for protein folding, and so on and so forth. Okay. All right. Yeah, we could like come back at 10, like a 5-minute break, and then I wrap up in 30 minutes.
5 minutes?
5 or 10 minutes is fine, whatever. Because I think it's good to stop right now. It's an hour and a half, right, June, this lecture? Yeah.
Please take a seat and
okay, so I'll wrap up here. I'll take maybe 20 to 30 minutes. The last two topics are related to a similar sort of theme, and that is that we would like to coarse grain things a lot, okay? So despite all these things I told you about, where's a good picture? This is the kind of model that we would like to end up with because we want to go to very big systems. The interest in my group and a lot of other people is not doing just a little bit better than atomistic molecular dynamics. We want to simulate systems that are, you know, effectively billions of atoms, so we want to get to very highly coarse-grained models. And this brings up a couple of issues. One of them is when you have these coarse-grained models, these very coarse-grained models, or really any coarse-grained models, how do you build in conformational change and tie it to something you can parameterize from bottom up, okay? And this is what we call multi-configurational coarse graining. The paper was published in 2019. And the idea is how can we represent something like this? This is a simple amphipathic helix, and you can see it's pretty highly coarse-grained, but it's still, even at that quite coarse-grained level, has an unfolded and folded state. Or it could even have more than just two states. And how can we do this? Well, this draws on a methodology that was originally developed by Aria Warshel that in my own group we utilized a lot to study proton transport, so reactive force fields that allow protons to go through water. And Aria originally called it empirical valence bond theory. It's really not necessarily empirical, and it's not necessarily in valence bond. What it basically is using linear combinations of functions, okay? And, I think I just turned, there we go, thank God. So here's the idea. Imagine that you have just two main configurations. So something like this. And in physical space, that means there's two free energy basins. And you imagine that those free energy basins are pretty well described by the coarse-grained coordinates, okay? That's part of the representability issue. You want to be sure that you haven't coarse-grained so much that you can't even see this, all right? But let's imagine that you do. Then the simplest example we can think of is coupling those, all right? And how would you couple them? Well, you could imagine that you would have these effective free energy surfaces for one of the basins and the other basin, but they'd be really quite different. And they may have actually been arrived at through different parts of the algorithm or even entirely different coarse graining methods. So maybe this one is the folded state that you get through simple sort of elastic network theory, which is sometimes used. This could come from multiscale coarse graining or inverse Boltzmann. This could be the unfolded state. And the idea is how can I connect them, okay? And you might at first think, well, this looks pretty trivial. It's a 2x2 matrix, just like in quantum mechanics, right? Mixing two states. You solve for this equation. If you invert it, what you can do is you can write down an equation for this coupling term, the thing that couples the two. That's the thing you don't know, all right? And if you knew the overall free energy minimum, in other words, the whole thing between the two states, and if you knew these coarse-grained representations in the two basins everywhere in terms of the coarse-grained variables, you could get this just by solving that equation. And of course, that's not going to help you very much because if you knew the full solution, why would you do this in the first place? It would be pointless, okay? So you're not going to know that. What you're likely to know is probably your coarse-grained models, okay? And probably something about the full answer, but not as a function of all of the coarse-grained variables, all right? Because then you'd have all the answer and you wouldn't need to do any of this. So the hypothesis in this work was that what we can do is we can choose the coupling function, you see here, as not being a function of every coarse-grained variable, but of just a few what we call collective variables. And that's what I'm calling Q. Now, it doesn't have to be a single collective variable, it would be some small number. And then the assumption, this is kind of similar to what Warshall did originally, is that, of course, at the atomistic level, when you have electronic structure going on all this, you don't know what these coupling functions are. So he assumed they were a function of a few variables that he could parameterize. We are going to say, well, what I can do for a select set of collective variables is, and again, we can use fancy techniques to find these collective variables. We can use machine learning. We can use all kinds of search methods. We can then use metadynamics to sample them. What we can do is get the free energy surface along those collective variables from free energy sampling. We imagine that we have our coarse-grained models for our two basins, right? This is the first part of the talk, was saying that I can have these things. I can project those onto a collective variable. The collective variable has to be a function of your coarse-grained variable. And then I approximate this coupling term by a function of only those collective variables, right? That's an assumption. Right? And so you do this, right? And this is now something that you can get at with less computational work than just solving the full problem, all right? And in fact, you can also iterate this method. So if you know something about these free energy surfaces, right, as a function of just the collective variables, you can iterate and keep improving the method with this a tuning parameter. You keep iterating this thing to get closer and closer to the all-atom result. And I should say, since, I should say this, I should have said this earlier. Everything I've been telling you about is what we call bottom-up. It doesn't necessarily have to be bottom-up. In other words, you could feed models into it. I could have a model for the all-atom interactions, right? Some sort of, I don't know what. I mean, something. You don't have to do the full simulation, right? I could have a model for these coarse-grained things. The formal structure of everything I'm talking about can all be applied to more sort of top-down type heuristic models. I'm casting this for you today as how you would do it if you can do the fully atomistic calculation, at least parts of it. And so I'll show you how this works. This is dodecaalanine. And you can see that, here's the folded and the unfolded basins. This is free energy as a function of what? This is radius of gyration. And I think this has to do with hydrogen bond contacts. So you see this free energy basin here. And this are the different sorts of free energy sorts of functions I could use to represent these basins. This is a folded state. This is using Boltzmann inversion. This is the unfolded state using Boltzmann inversion. This is the folded state using what we call a heteroelastic network model. And this is using the heteroelastic model for the unfolded state. It turns out that sort of the best representation is to use this for the folded and that for the unfolded. And then as I iterate this methodology, I get an answer that's not perfect. But actually you can see that along this order parameter, I get the two basins. They're a little bit more localized than the atomistic thing. And what's important is, I don't know if I have it here, sorry, is the transition barrier between them is really rather good. And I also have not been able to show it here, but as you look along other order parameters that you didn't include in this modeling, it represents pretty well what the atomistic model does. So I think this is a step in the right direction of doing very highly coarse-grained models that also have conformational change. They're not tied to one conformation. When we take that, when we include the virtual sites that I talked about to deal with solvent, we're really getting somewhere. We're able to have highly, highly efficient models that include solvation implicitly and conformational change. Okay, I'll finish up today with the fanciest sort of exotic stuff we're doing, but in some ways the most exciting and the biggest payoff. And this is what we call ultra coarse graining. Ultra coarse graining is a little bit different than what I've been telling you about. Ultra coarse graining is driven by the need and the interest in going to really high scales. When you want to go to the really high scales at the level of assembly of hundreds or thousands of proteins, you have no choice but to really coarse grain. These are actin filaments, right? You have to really coarse grain your proteins, very highly. So this is a highly coarse grain representation of the actin monomer. There are 12 beads representing, 30. I think there's 375 amino acids plus this nucleotide, the ATP, and you're representing by 13 beads, including the gold one. Okay, So, that's approximately 30 amino acids per coarse-grained bead. And so it occurred to me that, and this actually, the genesis of this idea, it shows how important sabbaticals and resting your brain can be, occurred in 2012 when I was here visiting McKinley for 2 months in the summer and had time to think. If the idea is that a coarse-grained model like that, as a start, you can kind of believe it that it's some Newtonian object, right? It moves around. These balls have interactions. You might be able to get those interactions from some of the stuff I told you about earlier. But you're being very naive if you think that that highly coarse-grained model can represent even, a big piece of what that protein's doing. There's a lot going on underneath the resolution of that coarse-grained model. Not the least of which, for example, is that gold bead is your ATP. This thing is hydrolyzing ATP. When actin goes into these filaments, it accelerates the ATP hydrolysis by 40,000 times. So that turns into ADP plus a phosphate group, and then the phosphate group can dissociate. So at this level of this coarse graining, actin is a great example. These beads have to have a way of representing a lot of physical reality. And back in the summer of 2012, it occurred to me, what we really want to use as what we call in mathematical language an isomorphic representation is the idea that these beads have internal states, like quantum states. It's not really, I mean, sure, of course there's quantum states here, but the idea is that in an abstract sense, every one of these beads, which moves around, the polymer moves around, also has inside it quantized levels that represent the reality they're trying to mimic, because you can't see what's going on at this highly coarse-grained level. 2 examples again, I told you about that one gold bead needs to represent what this ATP is doing. Another one in actin, this little loop here, is really important for binding together the filament. It's called the D loop, and it can be either folded or unfolded. And depending on which of those states it's in, it interacts with the other one. So that needs to have 2 states. And what goes on in those beads depends on the other beads. This hydrolysis is very dependent on that dihedral angle of those domains and also this distance here. So the internal workings of these beads is dynamically coupled to the conformations of these. And when these beads undergo change, for example, when that phosphate group dissociates, this is a very different electrostatic environment that influences all of those. So everything's coupled. Right? It still is much, much faster than trying to, this kind of a simulation here plus water is 1 million atoms. All right, still much, much faster. The basic idea is if I have a very coarse-grained model, so very few sites, I have a manageable number of states per site. Okay, that's still going to be a lot less than some higher resolution coarse-grained model where I have resolved every single amino acid. There's 375 per protein here. And that is going to be better, if I could do that, than doing all atom MD. So the idea with the altered coarse-graining, despite this elaborate picture, is this is going to win for you. All right, and I'll show you some examples. It also allows us to represent, this was a picture of a lot of the equations involved, so there's real rigorous theory behind this, at least the theory of generalizing all this force matching, what we call multi-scale coarse graining, of how to project out all of these states. But it can represent a lot of stuff. So I mentioned hydrolysis, protonation of amino acids, electron transfer, folding, unfolding, I mentioned that one, something like a ligand binding, or some region of the protein gets disordered. All of this stuff is not something that you will resolve in the coarse-grained model. It's very highly coarse-grained. Okay, but you don't want to forget about it. It needs to be in there. It's really important. All of this stuff is stuff we know about, plus there's more things. So the ultra-coarse-grained model is an abstraction of developing a classical simulation model that you have particles moving, the coarse-grained beads. They have average interactions, but that is modulated by internal state changes that represent realities like this. And of course, it's all coupled. The hard part is what in the world are the actual dynamical equations of motion for this? And we don't know. We don't know the answer. But we do know 2 limits. And I'll tell you about the second one. The first is where the changes in these internal states is very slow. ATP hydrolysis in actin is a good example. It's a slow process. And this is a lot like in quantum mechanics, what we call surface hopping. You go along moving on one electronic surface, and then you make a rare transition to another electronic surface. We can actually develop an algorithm in this limit. That's the slow transition limit. Or the other limit is, these big beads, they move pretty slowly, so what's going on inside of them with these states can always be in local equilibrium. They can always adjust. And that's a little bit like in quantum mechanics, adiabatic or Ehrenfest style dynamics. We wrote papers on both these, so this can be done. Okay, so I'm going to show you a quick example of this and then finish with some biology. An example is, again, go back to these one bead liquids, right? These I don't know, methanol or whatever you want to do. But imagine, though, that we want to do something more elaborate than just simulating the bulk liquid. Imagine we want to simulate an interface. We want to simulate a liquid-vapor interface. That's awfully hard with a very coarse-grained model where you coarse-grain away everything that makes the interface interesting. So at a start, we can imagine that our one-bead models are sort of schizophrenic. They have two states, right? They have one that tells us that I'm more in the bulk phase and one that tells me I'm more at the interface. And we have to have some rules for determining, are you at the interface or not? What's the simplest way of doing that? Count your neighbors, right? If you're deep in the bulk, you have a certain number of neighbors around you on average. If you're at the interface, you have approximately half that many. And so that's a local order parameter. So you can actually develop an algorithm that does that. You can do this for other things. You might have a molecule that changes its dipole moment molecularly, but when you coarse grain it to the particle, a single bead like that, that's gone. But that information can be built back into the state dynamics, that actually that bead has two different realities that represent what conformation is in. We've written papers on both those. Let me show you how this works. This paper was published in 2018, and again, Jay Hook is along with Alec and others in my group really the pioneers of this, very courageous. The idea is take all these liquids, not just methanol, which always seems to work for us, but all of them, coarse grain them into one bead model. Even benzene, that's pretty aggressive, right? So I'm going to represent benzene by one coarse grain bead and see if we can do the liquid vapor interface with this new idea. And what you first find is that the standard coarse graining that I think you'll learn numerically doesn't work at all. Why? Because even if you have an interface here, I should mention, if you've never simulated interfaces, the way you do it is in a periodic simulation. You have a slab of liquid. You periodically replicate in 3 dimensions, so you have the liquid vapor interface on both sides here. Then you be sure that is wide enough that you go to bulk-like behavior here. That's how you simulate. So if you coarse grain this the standard way, you're dominated by all these bulk interactions. There's very few at the interface. And that will dominate, and you'll get nonsensical results. So this is the all-atom results for these. You can see when I simulate, this is the high density you go through here. That's called the Gibbs dividing surface into vacuum. That's what this is, right? That's the density. The MS-CG for methanol isn't so bad, although you can see it's a metastable phase. It's not really a vacuum. Ethanol, total failure. It doesn't give any kind of separation. Acetone, some very odd fluid. And again, acetonitrile, these are 4 examples, is not good at all. But when I go to this ultra coarse grain idea, where now my coarse grain beads have really three internal states. The third one is not so important. It's the vapor phase. You don't interact with anything. But you have one that's in the phase boundary, which modulates. It tells you, I've got fewer neighbors. I'm in the phase boundary. I need to pick out the right forces for my coarse grain model from force matching. And then the liquid phase, when you build that in, you get different interactions. You don't need to pay attention to this, but look how well it works. I mean, it's not perfect, but these are 2 really hard examples. This is acetone and benzene. And you can see that the MS-CG, just the straight-up force matching, gives weird metastable sort of fluid-like phases where you don't have a vapor phase. This gives totally a vapor phase, not quite the right density maximum here relative to the all-atom, But this is a huge breakthrough. This is a huge breakthrough in being able to use very highly coarse-grained models and describe some sort of an interface. And it doesn't have to be a liquid-vapor interface. Excuse me. It could be the interface with a protein, or it could be interface with a hydrophobic wall. It could be anything. So this allows tremendous amounts of heterogeneity to be built relatively simply into the coarse-grained model. Stuart Jan Merink, and we keep seeing each other and keep talking about it. I think this idea doesn't have to be a bottom-up coarse-graining. It could also be applied to something like a Martini model, where you can use these ideas of ultra-coarse-graining to juice it up so it can do more. Okay, so let me finish up. Well, I want to be sure I don't take too much time with an application of this work. And you'll see where this ultra-coarse-graining idea came in. This is to the HIV capsid assembly. This story, some of you may have heard before, you've heard the lectures, but it's just come to final fruition now in terms of drug development. So let me tell you about this. HIV is driven by the production of these GAG proteins and, of course, the RNA of the virus. And the GAG proteins, when they're in the infected cell, will accumulate on the inner membrane here. They have a binding interface of the viral RNA, and they drive a bud. This is the cell membrane. It buds off. And there's this interesting sort of assembly in there called the immature lattice. And then the escort proteins, which I don't show here, come in and help cut that neck. This thing goes free. This is now the viral membrane. It's got some receptors on the surface that come along, which I am not showing. And it's called the immature virus. It's not infectious. At this juncture, HIV protease, which has been a drug target for many years, as an enzyme comes along and starts cutting up the GAG molecule. This green part of the GAG is called the capsid domain, and it undergoes self-assembly to encase the RNA and creates this virus capsid. This is now infectious. And it fuses with a new cell, not the same one, of course, injects the capsid. There's a kind of a poorly understood uncoding process and so on and so forth. This is how the virus works, basically. There's a lot of other stuff that goes on, but this is the core of it. So we felt that we could develop coarse-grained models for this self-assembly, in part because in vitro, without doing all the biology, you can just put the GAG molecules in a beaker, add crowding agents or salt, and you'll get assembly. All right, sometimes you'll get these capsids. And this is what they look like, this virus capsid. This is this maturation. There's the GAG. There's where protease cuts. Actually, there's more than that, more than 3. That's the capsid domain. The capsid domain dimerizes into a dimer, and then the dimer self-assembles into this virus capsid. There's about 1,200 proteins here. It's actually rather complicated. If you look closely, you see these hexamers. There's a hexameric lattice. Each hexamer has half of the CA dimer in one, the other half in a neighbor. The C termini are one shell below, underneath in gray. And then there are, in the perfect structure, 12 pentamers. These are not different proteins, just pentamer structures that close this surface. And of course, the RNA is inside of it. Although not always. You can actually make these without RNA inside in vitro. So we felt like we had the technology to do it. I'd be lying to you to tell you that everything was beautifully bottom-up coarse-graining. Like I told you before, we had to use a lot of data, did some top-down coarse-graining, and failed. Okay, the very first simulations we did were failures, in part. So these were the first outcomes of coarse-grained model of all this. It had some flexibility here, basic structure, basic interactions. There was some sort of clever stuff we had to do to make it all work out. And this is what we got at first. This is a sort of a phase diagram. This is concentration of this capsid protein, concentration of the crowding agent. The crowding agent is important to drive the assembly. And what we found was that you just never got good structures. Bizarre, kind of sometimes it looked like a capsid, but you'd always grow too fast, out of control. Especially in this domain up here, what those little snowflake things mean is that it grows, but it grows crazy. If you go down in here, it never grows, but it does do something really important. And this was the genesis of a real breakthrough. Down in here, we identified the nucleator of the lattice growth. What it is a trimer of 3 of these dimers. So it's a trimer of dimers. There's 1, there's 2, and there's 3, color-coded. They form little triangles. They come and they go, they come and they go. They have a binding and they have some lifetime. And down in here, that's all you get. You never get anything. But as you go across that boundary by either cranking up Crowder or capsid concentration or both, you start growing lattice. It's a nucleation phenomenon. It's classic. You've got a nucleator. It lives there metastably. If you push conditions the right way, boom, it goes. The problem is it went crazy. Control is something wrong. What we realized, and I should point out, this trimer of dimers is a little bit of a different view. That's at that vertex there in this lattice. So really the hexamers are not the fundamental thing. It's this vertex there. So that builds everything. Okay, what we was the conformational motion of this protein. And this is really important. The conformational motion of this protein here, these are loose linkers. So this is just one conformation that can have all kinds of conformations in solution. It turns out there's NMR data that I wish we had known at the time. we found it later. It tells you that. It actually says that only about 5% of the time, maybe 10% of the time in solution are you in the right conformation to add to the lattice. And the rest of the time you're in weird conformations, different kinds of things with certain time scales for going between them. Now the dilemma here, and this brings the picture of this really drives home the point of how ultra coarse graining can help you, is you absolutely do not want to try to explicitly sample all this conformational stuff. It's hard enough for just one protein, let alone 1,200 of them. Okay? But you want to build what's known into the model. So how that's done with the ultra coarse grain model, we stick with a model that has its basic conformation with some flexibility, but there's internal variables that go with it that switch on or off the interactions that say I'm in the right conformation and I'm not. All right? So when that's switched off, the underlying sort of ghost model looks like this, but they can't have adhesion. You've turned it off because that's representing, in reality, what goes on with the real protein. So this ultra coarse grain model allows us to actually build in that. Now, why is that important? This is entropy, right? So and I'll talk about this more. There's conformational entropy of this thing that was missing in that coarse grain model. And that entropy, when it goes in that lattice, is lost. So it's a delta S that you really need to be accounting for. And we actually can grow capsids. This is very interesting. This is a different kind of diagram. This is how much of you're in the right conformation. It's a knob. You can tune. The experiment says it's about here in reality. This is the time scale of the switching between those conformations. In coarse grain time scales, it's about 4 orders of magnitude faster than the growth process. And if you do that, I'm running here. This is when I've not got this ultra coarse grain modeling. You can see the crazy growth. When I do have it, I'm not showing all the proteins here. It's an extremely dense solution. I'm just showing the ones growing. You can see that the trimers are templating lattice growth. There's a kinetic funnel it's going through. So there's lattice growth versus curvature of the lattice, because when the proteins go into lattice, they have natural curvature. They need to be timed just right. If you don't time those just right, one will get out of control. Either you'll grow too fast and never curve, or you'll curve too fast and not grow fast, and you turn it like an onion, and it needs to be just right. And in fact, we can actually do that. So that allowed us to actually simulate capsid formation. All right. And it turns out that the capsids, we'd run these simulations. This didn't go all the way to closing this capsid, but we'd go over and over again. You get lots of different forms. It turns out that John Briggs a couple of years ago showed that in real viruses, you don't always get this perfect form. You get different things. So like this kind of fat one, like the one I was just showing you. And in fact, that's what we get. Okay, final story, and then I'll quit. I'm just a couple minutes late here. What's going on here is fundamental nucleation physics, if you will. Imagine you have an order parameter that tells you about growth of the lattice, of a lattice like that. Now, in reality, I have other order parameters, say one coming out of the screen that tells you about curvature or three-dimensional growth, but let's forget about that for now. These proteins, when they want to assemble, they start from floating around freely in solution. They're very happy entropically, right? They've got all that freedom. So when they start going into the lattice, delta S goes in the wrong direction, right? Delta S is negative, so minus T delta is positive. You get a line like that. Your free energy of the system is going up. But when they go into the lattice, they get all these protein-protein contacts. That's what a lattice is. So the energy is just right. So delta H is negative. It's going the right way. So a nucleation phenomenon is a crossover between the two. I'm sorry I can't draw with my pointer a smooth line. And the rate is some sort of an Arrhenius type law. So if you fiddle around with these, you do things right, you push that barrier so you can grow kinetically. All right. Now, what I'm going to tell you in just 2 or 3 minutes is that there's a new drug that's based on all the physics that's discovered by these simulations that tweaks this, but tweaks it in a very interesting way. I think most of you may realize that most drugs the idea is to inhibit something, right? Most drugs compete with a binding process. I think this is protease, right? So it competes with binding process and replaces what the bad actor wants to do, and it kills it. Okay. What the folks at Gilead did, they were insightful. They didn't know about our simulations, but they did know that this trimeric structure is important, and they realized that, well, if they can somehow create a drug that stabilizes these interfaces, they could not inhibit the growth of HIV, they could over-accelerate it. So it's a little bit like, you know, when you drive a car through a corner, like if you're a race car driver. Inhibition is, you know, you just don't even start the car. You never can get through the corner. This idea is stomp on the accelerator, make it go too fast so it crashes and burns. It never goes through the corner, okay? And you know, if you've ever driven a car too fast, there's a really fine line between going through a curve. I mean, I hope you've never had an accident, but you can feel it, right? You really need to go through the right rate of speed. So they did have the right idea that, you know, something that would actually stabilize something, and since it's a critical nucleating agent, since it's critically fast for this kinetic process, it's going to be incredibly sensitive. You don't need to bind a drug in every single bloody interface, just a little bit, all right? And you'll set things crazy. So our original paper really had the proper physics in it. We just published this paper actually before these guys here, even though they didn't cite us. That happens. We actually explained how this works. And again, this is the picture. Let me just keep going here. What it basically does is in fairly small proportion, the drug binds and it stabilizes, especially these trimers, a relatively small fraction of them. It's incredibly potent in this range. And this movie will show you as a function of drug loading, just going up to, I think, 5%. This is no drug. Similar to the movie I showed, I'm sure it's jumpy, it's not as great. But this is the natural growth of a capsid. This is as a function of drug loading. You can see this is much faster, and it's got holes. It's got pentamers in the wrong place. Too many pentamers, it's got holes in the lattice. And so what's actually happening with this drug is a whole new form of action that people hadn't really thought about. And I think that Gilead and other companies are really quite excited for virus treatments, because viruses all involve some sort of capsid, is accelerate that and make it go too fast and never form the right kind of capsid. And what basically you're doing is you know, by stabilizing some of these proteins, you fiddle around with the delta S and you shift that. By binding the interface a little more, you fiddle around with the delta H, you shift that. And so you actually get a much different rate, and it's exponentially sensitive. So this is quite consistent with cases with developing things where you don't have the RNA in. You get all kinds of, these graphs show pentamer inclusions. So the idea is that these drugs actually over-accentuate pentamers. This is a secondary action of the drug, that even if you do form a capsid that somehow encloses the RNA, they're leaky. They will uncoat in the wrong way when they infect a new cell, which is, you know, these are one of these bio things. I don't even know what the heck it says, but something there. You want the leaky. There's more leaky, all right? So this drug has a twofold action in it, but it's all tied to an improper kinetic funneling. And so I'm very excited about that. I'm gonna have to skip this last part. We're also doing something else. I think that's an example of a case where, you know, this coarse grain modeling has really made a difference. Maybe it was all by accident. We didn't know about the drug, but I really think it's made a difference. Let me just summarize. A lot of progress is being made for bottom-up coarse graining. I think that you know, we're going to you know, provide options for people in the future. I told you about the reactive coarse graining, but there's some additional things I didn't get to tell you about. We figured out how to embed a QM model in terms of an MM, but the MM has been coarse grained, so QM with a coarse grained environment. This is rigorous, it's not ad hoc. The reason this is important is in QM-MM, every configuration you have to do a quantum mechanical calculation. That's painfully expensive. So if you can coarse grain the MM, you're going to save an enormous amount. For those of you that probably don't care, you know, every theory should have a quantum, you know, quantum mechanics is correct. We actually did this quantum mechanically. We've made the next step of trying to go mesoscopically, where we don't even have coarse-grained beads representing particular pieces of molecules, but more like blobs. This was published. And this is the last thing which I would mention, where we use now coarse-grained simulation to then go back downward in scale to bias atomistic simulation. All right, and I think that's very important. I'm sad to say we haven't yet followed up on this paper, which is two years old now, but I think this is very promising. So, and that's, well, I'm not going to talk about all this and run out of time. Okay, so these are most of the folks that have done the work. I think I've missed one or two. Alec is here and here to help with the tutorials. These are the other folks. Alex and Alvin, which I don't show, have done the HIV work. Jay Hook has done amazing stuff on all of the fundamental developments along with Yaning. And so I guess this is a picture of a sunset in Colorado, and I think, you know, I'm going to finish with a kind of a message, and that is, you know, is it really, you know, have we just been beaten by these sort of top-down approaches? You know, is it all these years of sort of beating away on these very systematic bottom-up approaches, you know, is it the end? Well, I don't think so. I think bringing in more phenomenology, bringing in more sorts of theoretical ideas like the ultra-coarse graining, like virtual sites, like dynamic scaling, you know, these are things where you must do it at least conceptually from the bottom up, that, you know, sort of the merger of these things have led to very powerful new ideas that are not obvious how to do top-down, just sort of parameterized models. So I'm pretty enthusiastic about that. Anyway, that's it. I'm sorry I ran over a little bit. Happy to answer any questions you might have. If it makes you feel any better, I'm more tired than you are after giving an hour and a half lecture on jet lag.
So questions? Okay, there are many questions. But, I mean, we have just 10 minutes for question, maybe.
Yeah, because we want to give them time for their computer modeling.
Thank you so much. Very beautiful. I'm almost a newcomer to the field. In the little talk they allowed me, I tried to overcome a little dualism that is in science in between inference, machine learning, and modeling.
Yeah.
Here I feel that there is even a deeper dualism in the scale of simulation. Coarse, precise, even domain,
sure.
That I also treat. Well, I would like to spend a word also in this sense. Do not compete, but hybridate.
No, I agree.
When I project overcraft or flight, I do fluid dynamics precisely in the very point when there is a binding or interaction, like in a molecule. But elsewhere, you don't need the same precision. So if you do domain, far away, coarse, approaching, and precise, and you can mix together, instead of dice, you peel Lego, as I was saying a couple of days ago. So you cooperate instead of compete. You may increase your resolution, because if you do too precise, you lose in computational cost, and in errors, in computational errors. If you do too coarse, you lose in precision.
Right.
You should balance the two. And
No, I agree
that
with
could
you.
be my little contribution if I enter some collaboration with some of you. Thank you.
I agree. I think nothing that I talked about today precludes a multi-resolution approach. There are some very important technical issues, though, in a multi-resolution. If it's concurrent, in other words, if they're running at the same time, the highest resolution is always going to usually dictate your time step, your numerical effort. And actually, if you do it in a bottom-up sense of sort of eliminating degrees of freedom in certain regions, not only will that influence those regions, but it will also influence the fine-grained region, right? If you integrate out stuff over here, it's still so if people can overcome those problems, I think that I should have mentioned this as another frontier is concurrent multi-resolution simulation. I think it would be great. Yeah. Yep.
Hey, I was wondering how you choose the mapping in your ultra coarse grain model.
Yeah, okay.
I'm sorry for my
You
voice.
got the words out. I'm sorry. I guess. We do have algorithms for very highly coarse-grained beads by just looking at basic motions of the protein, even just like normal modes, and then you define the overall resolution you want, all right, how many beads, and then those beads adjust themselves to mimic that motion. But where we haven't yet gone, and for some reason it's been sitting there for a number of years, is two things. One is where you don't tell it how many beads, right? It figures out how many beads you need. And I think they're machine learning, right? Like if you can look at, relative entropy measures like that. The other is fitting the electrostatic surface. It's one thing to fit the motion, but you would also like your beads to represent the electrostatic surface at a coarse grain level. And we haven't done either one of those, but there are algorithms for doing it as opposed to just insight. And in some of these proteins, insight has tended to win. You just know, you look at actin, you can see the domains. I mean, you just, okay, yeah.
Hello.
Yeah.
First of all, thank you for the talk. I was curious about the parameterization of the ligand in the last part of the presentation when you told about the stabilizers of the HBU capsid.
You mean in the HIV part?
Yes.
Yeah.
Yes.
The parameterization of the model?
Yes.
Yeah.
How can
The model there, and again, I tried to say this, but I'll say it again. We did not use bottom-up coarse graining there. We used knowledge-based stuff. What's subtle about the model, I went all the way back to the beginning. Forget it. What's subtle about the model is that it is a multi-resolution model, actually. Because these proteins pack into a lattice, their granularity matters at packing. So in the short-range interactions, we have carbon alpha level interactions, which are not expensive, right? Short range, you can have a cutoff, so you don't have some. And then long range, we only have 3 interactions, as C terminus with C terminus, N with N, and N with C. That's known experimentally, and there's tons of data about the different packing. So we use a knowledge base for that as a start. And what we're doing right now is then going back, and that model really works pretty well, but we're going back and using it to refine with atomistic MD and actual force matching. But for the broad questions we were asking in the HIV case, this semi-top-down approach actually works pretty well. I'm not a purist, like I use top-down. I mean, it's not like that people misunderstand. I'm not trying to, I just think it's very important to have at least the fundamental representation. I'm not saying everybody should use it all the time, but I think it's important to have that. So, if you want to take a look on our papers, you can see more description of that on.
There are more questions. I have one question
Sure, yeah.
about the first part of your talk about the virtual site and the lipid, and that you have modeled this virtual site as one virtual bit. And then you also said future application also for proteins, and the possibility to use this virtual sites or these virtual bits also to describe conformational changes of protein.
Absolutely. Right? If you, one way to look at the virtual sites is kind of a primitive way, but just gives you more ways to represent interactions, right? You have another thing, or more. There's a subtlety though that if the more there's this really perverse aspect of bottom-up coarse graining, and that is that the more highly resolved the model, the more complex all these possible interactions can get, and it gets harder and harder. And at some point, it's not much better than just doing all atom. So in many ways, you want as few sites as possible. But you could definitely use more than one virtual site. In a virtual site, if you imagine trying at a very coarse grain level to get the protein to do what you want, if you have another thing that you can parameterize that will drive you that way, then yes, absolutely. So that's perfectly correct. Solvent was the obvious thing, but and Alec, and again, I keep advertising his paper because this machine learning stuff is beginning to sell me this idea. He uses these generative adversarial networks, right? So there are additional ways of parameterizing virtual sites. So, and I think that could be one. If you have some information on the conformation.
Yeah, because some conformational changes quite standard in proteins. So you can model these.
Absolutely. That's right. But of course, it's just like everything. If you don't know those, like, how do you discover them? So that's another thing. But, yeah. Okay.
Thank you.
Greg, thank you very much for your talk. Related to the ultra coarse grain, I really enjoyed the idea just to combine 1B different quantum levels and scan the different properties. I would like to have your opinion about if it's to implement this to improve the solvation model, just to in the beads that represent the waters, to include dipole moment, using also a variational approach or this kind of stuff that can be more accurate in identify waters that have different properties depending on the position in the models that we have, in order to improve it, to fill this gap that you mentioned about the solvation model in coarse grain.
I think that it's possible, maybe it's in contradiction, that when we put the ultra coarse graining into beads, and part of these internal variables tell you about your solvation, right? They tell you that you're solvent exposed or you're not solvent exposed, or you have certain neighborhoods, that maybe we won't need the virtual sites, right? Okay, or we could put the ultra coarse grain beads in the virtual sites. So in other words, there's just this huge number of things that we can imagine doing. But you hit it on the head, is one of the very next things for the ultra coarse graining is to build in solvent environment as a part of this goal of getting rid of explicit solvent, right? And the two obvious are some solvent exposure measure, right? So an alanine is very different if it's exposed to water than if it's buried. Yeah.
So no more questions, and thank you again, Greg. Now I would like to invite here the other organizer, just to make the.
So, students, so we approach the end of the school. We still have the practical session, but we are moving to the other rooms, so the computer rooms. So just we would like to thank you, all of you, for coming. Again, waiting the Paulo switch with the front page slide of the school. We want to, acknowledge, l'Università della Svizzera Italiana of Lugano, their staff that make available, they make possible the organization of this school, okay, giving us this beautiful aula magna for 1 week. It's not easy to have this availability. Also the computer rooms, Novartis and the Hasler Foundation, CSCS, Silicon Therapeutics, a cost action that sponsor the school. Of course, the SECAM is a major funding agency of this school. Thank you for coming. In particular, thank you all the speaker, Greg, all the great scientists that we have. It was not easy to get all of them here. We are very honored and pleased that they accept our invitation. I hope you enjoy the whole week. It was an opportunity for you to open your mind, to understand that things can be done in an accurate way, and you can approach to your research project in the best way. This was the main goal of this school, to get you closer to the best science that we have in the different fields in computer simulations applied to DNA and proteins. So I thank you in particular also my group, particularly Stefano Ragnolo and Paolo Conflitti, that was the two guys that operatively set up all the machines, so they did a great job. They are very so stressed. They need some vacation, I think, some holidays. And I want just to leave the microphone to Daniele and Francesco for concluding remarks. Now we have copy feedbacks, and then we'll move to the computer room for the last practical session of the school. Thank you.
First, would like to thank you, Vittorio and Francesco, for the nice job that they have done with me, and also all of you for to be here, this school, and I hope that this school can help you in the future. Also, in particular, because in this school we have touched different approaches coming from different fields, and so now you have a wider view of the computational and theoretical approaches, and this is maybe very important for your future and for your career. So good luck.
Well, so they almost said everything, so no, I'm really happy about the school, and it was a very tough work, but I hope you enjoyed it. And of course I want to thank you, because without you, of course, there will be no school. So your feedback will be a very low voice today, and we will wait for your feedbacks, because they will help us to improve what's going wrong, or to keep what was right during the school. And I hope really you enjoyed it and opened your mind, as Vittorio said, because it I think for you it has been a really important occasion. So we when we were younger, we did not have this kind of opportunity. So this was the main purpose of this school. So to give you an overview of what can be done in the computational biology and chemistry world, and that's all. So thank you, and see you.
So very last practical information for you. Photos, slides that the teachers will give us will be available on my Facebook page of my group, research group, and Twitter as well. So we find the link as soon as we collect all the slides and all other information, photos. So anything related to the school will be, so just check on internet, will be made available there, including the videos. The videos are available already on the YouTube, and will remain there. I guess. So you will just go there and download whatever you want, all the materials from the school. Okay. So thank you, everybody.
Thank you.
Just have a quick coffee break, and then move to the room 156 for the last practical session.